All right, we're going to go ahead and get started. Today, we will probably finish up all of the formulas for the gas laws. There'll be a couple of more things that we do. Um, I will probably show another crash course video just to separate ideal gas law, ideal versus real, and kind of talk about that in a few minutes. But for right now, we're going to spend a little bit more time with Avogadro's law today because there is a little bit more to do with that with gas laws. I'm gonna refresh our memory about gas stoichiometry today. Um, converting from like liters of gas to moles back to grams and things like that. We'll do a couple of those, and then but the main thing we're going to focus on today is the ideal gas law, which I have it written in green on there. It's pressure times volume equals nRT. N stands for moles, R is the universal gas constant, and T is temperature in Kelvin. Um, and I'm going to show you why I choose. This really gets into the reason why I said I choose to use atmospheres for pressure, and then also why we have to use Kelvin for temperature, because the universal gas constant that I want you to use and not necessarily memorize, but the one that's on your reference packet has those units in it, and that's why it's important to always convert to those. All right, so we will go through and look at those things today. Oh, there it is. All right, so first thing, ideal versus real. So there are two ways to look at gases. We can look at them as being the perfect situation, which is nice because everything follows the rules and all of that. Or we can look at it as what really happens in the real world. Fortunately, a lot of the time, and for a lot of gases, especially low molar mass gases, they're going to act very closely to the ideal. Um, the only time we have to really start kind of thinking about real gases uh, and things that are happening with real, where we have to really take into account pressure and volume changes for a gas, is when we're looking at a gas that has a higher molar mass and things like that. Um, so let me do this. So these are some things that we need to know. All right. So an ideal gas obeys all the assumptions of kinetic theory. Yes. Yeah, I would. All right. So an ideal gas obeys all the assumptions of kinetic theory. So you remember the 6 assumptions that we went through yesterday. Things like they're all made of tiny molecules, that they're in constant random motion. They can expand to fill their container. Um, gas molecules have no attraction for each other. And then, the big things that ideal gases obey that real gases don't is that the molecules have no attraction for one another, and that that the collisions are elastic, that 100% of the energy is maintained. All right. Now, for what we know in the real world is no gas is perfectly ideal. Ideal doesn't exist. All right. So I'm not really going to add anything to that. But I'm trying to think of how the best to say that. So, if you just like no ideal gas exists, just like no ideal machine exists. There's no machine that is 100% efficient. There's always going to be some loss to friction, some loss to just mechanical or things like that failures. And in a gas, there's always going to be some energy lost due to those collisions, and there's going to be the fact that gases actually do have volume. Molecules actually do take up some space, so there are going to be a little bit of there's always going to be a little bit of compensation that we have to make for size. All right. So I guess the big thing is all gases take up space and interact with molecules. Remember, we do have these interactions of intermolecular forces between molecules, and all right, that every molecule, because it has a certain mass, because it has electrons, because it exists, will have intermolecular forces. Some of them will be very strong intermolecular forces, some of them will be weak. And then molecules themselves, because they have protons and neutrons in them, they are going to have mass. That mass has got to take up some space, so it's going to have volume as well. All right. But gases will act more ideally, will behave more ideally if they're in the right conditions. And those conditions are based off of temperature and pressure. All right. So this is kind of getting into where we're starting to make that distinction. A real gas does not behave like ideal gases at extremely high pressure or temperature. So, and I want to kind of break this down as to why. So, if I put a gas under high pressure, what am I going to cause the molecules to do? Are they going to be closer together or further apart? High pressure. I'm pushing pressure on it. All right. So at high pressures, the molecules are going to be real close together. Is a gas free to move when the molecules are close together? Not as much. All right. And then at low temperatures, what happens to the motion of molecules at lower temperatures? They slow down. So this does kind of make sense. At high pressure and low temperatures, the molecules aren't moving as much. So they're not acting as much like a gas. They're acting more like a solid or a liquid. All right. So this statement, I actually like to say it another way. I like to put it more in the positive light than the negative light. So the way I say this is gases act most ideal at low pressure and high temperature. All right. So low pressure, the gas molecules are spread far apart. High temperature, the gas molecules are moving really fast. So when we put it in that context, we recognize that since the gas molecules are moving extremely fast, they don't interact with each other as much. The intermolecular forces are kind of negligible at that point. So they're not going to slow each other down. And then at low pressure, they're so far apart, they're far enough apart that the intermolecular forces aren't going to interact there as well. So you kind of overcome the two things that hang it up from being an ideal gas when you increase the temperature and decrease the pressure. All right. And then those next two statements are really just explaining why they act ideal at low pressure and high temperature. All right. Again, because the molecules are spread far apart at low pressure, So there's less chance of them interacting. They're not going to collide as much. And high temperature, the molecules are moving faster. So the interaction is going to happen in less time. So there's not as much time for the interactions to occur. All right. All right, that one just kind of restates. All right, so we have this thing called the ideal gas law. Ideal gas law is a formula that allows us to calculate pressure and volume, assuming that the gas is going to act like what kinetic molecular theory predicts it will act. Now, I will say this: most of the time, ideal gas law is going to give us an answer that is perfectly fine, because pressure and volume are already corrected for in this, in that they're going to give you more room for pressure than you would need and more room for volume than you would need. So for 90% of the calculations that are done, ideal gas law is just fine. There is an actual formula for what's called the real gas law that we can actually put in conversion factors to make sure pressure and volume end up exactly what they need to be. But then whenever you go into production for whatever type of pressure vessel or tank that you're building, you're going to make it a little bit bigger, and you're going to make it to handle higher pressures than you expected anyway. So it just works out that we can actually just use this and not have to put in those correction factors. All right, so the P in PV equals nRT. P is for pressure. Now, I'm going to make a couple of corrections here. So pressure, I want us measuring pressure in atmospheres. Volume, I want us to measure volume in liters. Temperature has to be in Kelvin, and N is going to be in moles because it doesn't have a choice but to be in moles. All right. But this is the only formula that we've done through all of these that actually has to have the units exactly what they are. So pressure has to be atmospheres, volume has to be liters, temperature has to be Kelvin, and N has to be moles. The reason why is because the R constant that I have for you, and if you look in your periodic table reference packet, if you look on that second page, the R that's listed is the one that I listed. And if you notice, the units that it has is liter atmospheres mole K. This is a conversion factor that we're using just like whenever we used the heat of vaporization was calories per mole or calories per gram, things like that. We're just using this to cancel out other units in the problem. All right, so if we don't use the right units for pressure, for volume, for temperature, you get a number that means nothing. All right, so R is the universal gas constant. It allows us to solve for pressure, temperature, volume, or moles, depending on what we're missing. But the R that we're going to use is 0.0821 liter atmospheres over mole K. Liter atmospheres over mole K. So if we are given pressure, temperature, and moles, we can solve for volume. If we're given temperature, volume, and moles, we can solve for pressure. And if we're given pressure, volume, and moles, we can solve for temperature then. So it's a nice little equation. And the other difference between this equation and what we were doing yesterday. There's no before and after in this. This is a instantaneous look at the gas right when it's happening. So it's not one that has the before and after situation. All right. So take out your worksheets from yesterday, the packet that I gave you yesterday. We're going to look at a couple of these questions. All right. Now, I do want you to notice on this sheet, I gave you 3 different R's. I'm not going to use any of these. I'm going to always convert to the right thing. What I do want you to recognize on those R's is notice that this one, the 0.0821 has atmospheres. This one, the 8.314 has kilopascals. And the one that's 62.4 is millimeters mercury. The pressure, the units that the pressure in or in each of these is why this number changes. Just like the calories versus joules relationship that we were using earlier this year. All right. Now, so question number 1 says, how many moles of oxygen will occupy a volume of 2.5 liters 2.5 liters at 1.2 atmospheres and 25 degrees Celsius. All right. So we have a pressure, 1.2 atmospheres. We have a volume, 2.50 liters. Moles is what we want to know. We have an R, because this is in atmospheres and all of that, I'm going to use 0.0821, and that's liter atmosphere over mole Kelvin. And then I'm going to scroll this up just a little bit so that I have room to write. All right. And then temperature is at 25 degrees Celsius. So I need this in Kelvin. So that's the only conversion I have to make. So 25 plus 273 gives me what? 298. All right. Now, the formula that we're using is PV equals nRT. We're solving for N, so I need to get N by itself. Best way to do that, again, is to divide by RT here. So that's going to cancel it. And then I divide by RT on this side. All right, so my actual formula that I'm going to use, N equals PV over RT. Now, I'm going to go ahead and put the numbers in just so I can show you unit cancellation, but I'm not going to solve it. All right, so we have N. We have our pressure of 1.2 atmospheres times our volume of 2.5 liters divided by our R, times our 298 Kelvin. All right. Now, just a couple of things before you actually solve it. I just want you to understand why we know that our answers will be in moles. If you're paying attention, this is one of the mistakes that I've seen students do in the past, is students want to put the problem within this little units here instead of actually using PV equals nRT. They try to put numbers into that. That's not what we're looking for. What this solely is for is I have liters divided by liters. I have atmospheres divided by atmospheres. I have Kelvin divided by Kelvin. And so that leaves us with 1 over 1 over moles, which is just moles. All right. So that solving it that way gets you to your answer. Now, I'm going to stress the fact that I would much rather you always use this R constant rather than switching between the different R constants. All right, so like for number 2, I'm only going to point out one point, is number 2, it gives us pressure in millimeters mercury. Well, for us to use this R constant, we have to get it to atmospheres. So instead, I would use 720 times 1 atmosphere over 760 mmHg, and then get my pressure in atmospheres instead. And then I would just use that for my thing. So 720 divided by 760. So that gives us a pressure of 0.947. All right. So 720 millimeters mercury is 0.947 atmospheres. And that's kind of where I would stick with it. So that way I'm still using the right universal constant for R. All right, that's why. So I'm always using this one. There's no need to memorize the other ones if I'm going to give you this one in your reference packet. So use the one that's always going to be available to you, is what I'm telling you. All right. Now, so kind of moving on, we're going to go back to Avogadro's law a little bit. Avogadro's law is where we ended up yesterday, where we were talking about that it's going to be a volume mole relationship, or it's a volume mole relationship or a pressure mole relationship. All right. So putting all of these putting Boyle's, Charles, and Guy Lusset together is what gave us combined. Putting Avogadro with all the other ones is where we ended up with the ideal gas law. All right, and that's so all of these are very important because it allows us to look at a gas and it allows us to determine a pressure, a volume, or amount of material based on a certain temperature and based on specific conditions. So Avogadro's principle, Avogadro's law, basically what he discovered, and I didn't write this out yesterday, I just gave you the numbers yesterday and the formulas yesterday. Avogadro's principle or Avogadro's law says that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So what he established is, if he had a container that was a volume of 22.4 liters. What he found out is that at 1 atmosphere of pressure, at standard temperature and pressure, at STP, he found out that this container will hold exactly 1 mole of a gas. And then, so if this was, if in this case, if it was helium, he tried it. He tried it with hydrogen. He tried it with oxygen. And what he discovered each time is that at STP, those gases was always ended up being 1 mole that it could occupy, maintaining that pressure. If you went higher than that pressure, that meant it had more moles than that. If it was lower than that pressure, it had less than 1 mole. All right. So remember that moles is basically a description of a number of particles. 1 mole, just to kind of. So if I say it like this, 22.4 liters of a gas equaled 1 mole, and that is a specific number of particles, 6.022 times 10 to the 23rd particles. Now, when he was doing this and all of that, how he came up with that number, I don't know. I can figure out how he came up with these two numbers. But to know that that was how many atoms it was or how many molecules, I don't know how he did that, because apparently a much smarter person than I'll ever be. But that's just kind of where it goes. I guess if I really wanted to read the research and all of that, I could figure it out, but I don't want to take the time to do that. I'm sure you don't either. All right, so he gave us this formula, V1 over N1 equals V2 over N2. We got that yesterday. There's no need to copy it down again. But because it's at standard pressure, we also can use it in relationship to pressure. All right, so we can use it either way. We can use the number of moles is going to be directly related to pressure. It's going to be directly related to volume. So there is a direct relationship. So if the amount of gas increases, the volume will increase and pressure will increase. If the amount of gas decreases, then the volume or pressure will decrease. All right, moles is amount. All right, nothing to copy off of this one, just kind of showing you. So I use the bunnies because bunnies like to repopulate. All right, so we start off with 2 particles. Those 2 particles multiply. We end up with more than 2 particles, and then they multiply again. And so at each level, the volume-mole relationship stays the same. The fraction stays the same. It's just the numbers are different. That's kind of like saying that 1/2 is the same as 2/4 is the same as 4/8. All right. All of those are still 0.5, no matter how you look at it. All right. So where do we really use Avogadro's law? And this is where it ends up being different from yesterday's stuff. We really use Avogadro's law for this concept of molar volume. Molar volume for a gas is the volume that 1 mole of a gas occupies at STP. I've given you the relationship before that 1 mole of a gas will occupy 22.4 liters at standard temperature and pressure. So we can use this as a conversion factor for both stoichiometric equations and Avogadro's law problems. And it really just depends on how our brains perceive the question as to how we approach the answer. All right, so we're going to look at a couple of examples, and I'm going to actually work through these all the way so that we can look at it. So example number 1 says, calculate the volume of 0.881 moles of oxygen. Calculate the volume that 0.881 moles of oxygen will occupy at STP. So we know it's oxygen gas. So N1 is easy to get. N1 is 0.881 mole. V1 is what we're trying to figure out. All right. Now, we're given that this is occurring at STP. So what would my N2 and V2 be here? What do we know is the circumstance for at standard temperature and pressure? One mole is what? So even though that's not the condition, we can actually use this to set up the relationship. So I can use that and solve for V1. So, I can do N1 over V1 equals N2 over V2. And I can plug in my numbers and I can solve it. Or I can do this more, treat this more as a stoichiometry problem, dimensional analysis problem, where I say that I have a given of 0.881 mole O2, and I know that I have for every 1 mole of O2, I have 22.4 liters. And so I can get rid of moles here, and I get my answer in liters. Now, if I was doing this, I would use this setup because I really don't like having to manipulate equations. All right. This one, I don't have to manipulate anything. I just establish a conversion factor based off the material. Standard temperature and pressure. Standard temperature is 0 degrees Celsius. Standard pressure is 1 atmosphere. But we established that there's a relationship at STP. 1 mole always equals 22.4 liters. All right. That's an established constant. All right. So we can use it either way. I just would typically prefer to set it up like that. All right. So you can go ahead and try to solve it if you wanted to solve it the other way of actually, let me write this the correct way. Sorry. V1 over N1, V2 over N2. So if I write this, V1 divided by 0.881 equals all right, so you could go 22.4 times 0.881 divided by 1, and that's your answer. Or you could do 0.881 times 22.4, and there's your answer. All right, slipping over to the next page, just showing you like I said, we could do it both ways. We could solve it as dimensional analysis. Like I said, I would have set it up this way. 0.881 times 22.4 gives us 19.73. Or if we set it up using Avogadro's equation, it's the same thing. It's just instead of being an equality, I set it up as a more of a formula. So we end up with 19.73 liters. Either way gets you the same answers. So just know that like last week, there's more than one way to get to the same answer. All right. Now, I would like you to try this one on your own and see what you get. So how many grams of nitrogen will be contained in a 2-liter flask at STP? You should be able to get to moles of nitrogen easily, and then you need to convert moles of nitrogen to grams of nitrogen. All right. So again, two different approaches we could use. I can use dimensional analysis, which is the way that I would probably go because that's just kind of what I'm programmed to do. I don't have to memorize a formula for that or anything like that. So I can use my molar constant that 22.4 liters is 1 mole. So I can go from 2.0 liters to moles of nitrogen. And then here, where did I get 28.02? That is the molar mass of N2. Remember that one nitrogen atom is 14.01 grams. So all right. So the molar mass of an N2 molecule is 28.02. Notice I use it, both of them, and we get there. So now looking at our solutions, going through using dimensional analysis, we would have ended up with 0.89 moles of N2 that we multiplied by 28.02 or 28.01 gives us 2.5 grams. If we did it the other way, we would get the same answer both ways. All right, we're going to end up with 0.89 moles both ways. 0.089 moles. All right, and again, for me, just the dimensional analysis way is the more preferred way, just for me, because I don't have to really think to do that one. I just set up my ratios and go. Whereas going through here, I have to do some manipulation to get N1 by itself. All right. So a couple of definitions. I'm not going to ask you to copy everything off of these. So one definition that we need to know to deal with gases is diffusion. What I would write off of this is diffusion is the movement of particles from an area of high concentration to an area of low concentration. You've all experienced diffusion before. So if I had some Axe spray stuff or body spray and I sprayed it just one squirt over here in this corner, eventually you would smell it in the whole room. Or if one person in this room has gas, it would probably spread, even if you try to sneak it out. All right. Which happens a lot in the hallway right there when I'm standing outside. Oh, yeah. So that's they spray it in one spot and it spreads to the whole room. All right. So that's what diffusion is. All right. Eventually it's gonna reach equilibrium. It's gonna spread throughout the room to a point that you don't smell it as strongly anymore, or you don't even smell it anymore. Kind of that point where you get nose blind to it because you're used to it. It's kind of mixed in with all the rest of the air. All right. The other kind of things that we need to know, entropy, you probably already know this definition. Entropy is just randomness. So all gas molecules experience entropy. They're very random. There's no organization to them. And then the other definition is a fusion. A fusion has more to do with, like, if you have a balloon, and if you've ever gotten like a helium balloon, and it's just one of these regular balloons, one day it's nice, it's firm, it's big, and then the next day it's real tiny. And that's because helium molecules are very, very small. So even though there's not necessarily a hole in the balloon, they can escape in between the molecules of the rubber or the latex that it's in. All right, that's why the mylar balloons hold up better than the latex ones, because the mylar balloons, the particles are closer together, so the helium can't escape as easily. All right, but they still escape. That's the same reason why even if your tires on your car don't have a hole in it, the pressure gets lower from time to time. It's because the air molecules are effusing out of it. So, like if you go to certain tire places, they will insist that you fill your tires with nitrogen gas. All right, so they can charge you. I do want you to keep in mind that regular air that comes through a compressor is 70% nitrogen. So they are ripping you off. All right. They're not going to give you straight nitrogen in your tires. They're going to give you compressed air and say it's nitrogen in your tires. All right. So two more laws. Basically, what Graham's law. I'm not going to give you the formula for Graham's law because the formula has a square root in it and all of that. But what we really need to know, this is what we need to know about Graham's law, and it's actually pretty logical. If you have particles that have a very low molar mass, they will travel faster than particles that have a high molar mass. All right. So you can put it in context to a football players. Typically, your biggest guys on the team are not your running backs or your wide receivers. They're the ones that don't have to run very far because they're playing line positions because they're not going to move as fast as the guys with longer legs and that are skinnier. All right. So, hydrogen is way smaller of a molecule than oxygen. Hydrogen will escape out of a container faster than oxygen will. Specifically 4 times faster, but you don't need to know that. All right. And then the last one, and this one we will do some calculations with, Dalton's law of partial pressure. So Dalton's law of partial pressure says that if you have a container with a mixture of different gases in it, the total pressure of that container is the sum of all the other pressures in it. Dalton's law can also be related to moles, so that the total number of moles is equal to the sum of the moles of materials in it. All right. So now we can extend those for as many types of particles that we have. So kind of ways to think of it is we say that atmospheric pressure is 1 atmosphere. But we know that we have oxygen, nitrogen, we have carbon dioxide, we have water vapor in the air. Whenever we look at these and we're trying to say, how do we get this 1 atmosphere? Well, I know that nitrogen is 0.7 atmospheres because it's 70% of an atmosphere. All right. Oxygen is going to be like 0.28 because oxygen is about 28%. And then these other ones are going to come up to fill up the other 2%. So carbon dioxide might be 0.01 and water vapor might be 0.01. All right. And so if you total all of those up, you should get pretty close to 1 atmosphere. All right. And that's Dalton's law right there. That these are my partial pressures. This is my total pressure. All right. Same thing with moles. We can count number of moles the same way. All right. So let's look at the example in our packet. You should have some questions that talk about partial pressure and Dalton's law. All right. So says, what is the partial pressure of hydrogen gas in a mixture of helium, hydrogen and helium if the total pressure is 600 millimeters of mercury and the partial pressure of helium is 439 grams. So in this statement, in this question, we have a P total that equals 600 millimeters of mercury. All right. We have a pressure of helium that equals 439 millimeters mercury. And we want to know the pressure of hydrogen. So if I have this equation that P total equals P1 plus P2 plus P3, etc., and I'm trying to solve for the pressure of hydrogen, I could say that pressure of hydrogen is equal to P total minus the pressure of helium. Yeah, this one, Dalton's law is easy. Now, I can show you where it gets maybe a little bit more complicated, but it's still not that bad. Because there is going to be a question in your Chem 101 that relates to this one. So if you look down to the bottom of the page. All right. So down here at the bottom of the page, when we're conducting labs and when they're trying to find out the pressure of a gas that's created in a chemical reaction, we do something called, the lab process is called collecting a gas over water. All right, and this is where I wish I still had some of my equipment that is somewhere on campus that we can't find it right now. All right, because I would actually show you this demonstration. But basically, you have this lab set up where you have a bucket of water, and then you have a reaction tube that's inverted, and inside that reaction tube, you have a piece of metal. All right, so I have a piece of metal like right there, and then I have acid in this tube or whatever, and it reacts with the piece of metal, and it forms bubbles, and then you get a captured gas in there. All right, and so we collected the gas over water. Well, we can determine the volume of that gas based off of how much space it occupies in that tube. And so what we want to find out is what is the pressure of that gas, or how many moles of that gas do we have. So we have to use Dalton's law to do this. So looking at number 7, it says carbon dioxide is collected over water at 35 degrees Celsius. That's important for us to find out the pressure of water that water is going to apply. The total pressure of the system is 0.493 atmospheres. What is the pressure of the CO2? So when we're looking at this, there's 3 things that we want to, or there's 3 pieces of information that we have based off of this question. All right. So I have a P total is 0.493 atmospheres. I know that I'm trying to find out the pressure of CO2. The only other thing that I know I have in here is water. So I need to find out pressure of water as well. Now, right now, as it is, I can't solve anything. But they gave us this little piece of information that this occurred at 35 degrees Celsius. So I can look, and on these charts, and they'll always have a chart like this available if you ever need it. And in fact, in your reference table, all the way in the top right side, you'll see a water vapor pressure, millimeters mercury, in there. So you have a table similar to this at your resource. This particular one measures it in kilopascals. The other one, the one that I'm using the one that we would be using normally, measures it in millimeters mercury. All right. So I find 35 degrees on here, and I find that my pressure of water is 5.63 kilopascals. Huh? So the one here only does that. So the problem that you might have on the exam or test 3 is going to be between those ranges. All right. This one, I just pulled a table out of a textbook, so I had a larger table. All right. Now, so right now, I can sort of use Dalton's law at this point, but what's the first thing I need to do before I can use Dalton's law? I either need to convert to this one to ATM or this one to kilopascal. It doesn't matter which. I would probably do this one. All right, so 5.63 divided by 101.3 means that we have 0.0556 AT. All right, and then from there, I'm just going to go P total minus pH2O equals pressure of CO2. All right, and again, the only thing different on this one is we had to use information off this table to get one of our pressures. All right, so that is kind of it for that. Now, so just to kind of sum up gas laws in a manageable way, rather than trying to memorize every one of these equations, I would actually put it down to just memorizing 3 equations, or really, well, 4. So I would remember combined gas law because that takes care of Boyle's, Charles, and Guy-Lusset. I would remember ideal gas law. This is actually in your reference packet, so you don't have to memorize that. Avogadro's law, volume to moles or pressure to moles. Remember the gas constant over there. And then the only other thing that I would really include, and like I say, this one is not a hard one, is Dalton. Remember that Dalton can either be pressure or moles. All right. And so that's pretty much it. All right. So the only other concept that they have is stoichiometry in gases. All right. So there will be a couple of problems like this, and this is not a bad thing to refresh our memory on, is stoichiometry in general, mole ratios and things like that. So this is where we kind of put everything together. So it says, what mass of water is required to react with 15.5 liters of nitrogen gas? So if I go back to my little mole island sheet that I gave y'all, I'm starting over here in volume. I need to get from volume to moles, and then I need to get from moles of one thing to moles of the new. So mole A to mole B, and then I'm going from moles to grams. All right. So my stoichiometry problem has to have all of those steps. So I'm starting off here at 15.5 liters of NO2. How do I get from liters of nitrogen dioxide to moles of nitrogen dioxide? All right. 1 mole of NO2 is 22.4 liters of NO2. So now we're in moles. How do I get from, what am I going to use to get from moles of NO2 to mole of water, H2O? Mole ratio. So where do I find my mole ratio? In equation 3 to 1. So for every one of those, there's 3 of those. And then now, ultimately, I need to get to grams of water. So what am I going to use to get from moles of water to grams of water? Molar mass. And that's all we would have to do to solve it. Now, not so much concerned about you getting the answer, but I want you to go ahead and give me the setup and see if you can set up the problem for the second one. It says, what volume of nitrogen monoxide would be produced from 100 grams of water? So instead of looking at these two, we're going to be looking at water and nitrogen monoxide. So if you're check your setup, that's what you should have gotten because water and nitrogen monoxide are both coefficients of 1. Your mole ratio is 1 to 1. So 100 divided by 18.02. So we should, yeah, because that's the standard. That's the known constant. Yeah, I got approximately 124 liters, 124.3 if we stick to the right numbers at fix. All right, and now the last one. I'm going to do this so that I can see it all on there. So on the last one, and I know it's probably kind of hard for you to read from back in the back, it says if 42 liters of nitrogen monoxide is produced, what volume of NO2 reacted? So for this one, what I'm just going to kind of show you this one conceptually. All right, if 42 liters of NO, nitrogen monoxide, reacted, again, we have the whole 22.4 liters to 1 mole. And then we have our mole ratio of 1 to 3. So 1 mole of NO for every 3 moles of NO2. And then we do the 1 mole to 22.4 liters. And then that's going to give us our answer in liters. What I want you to notice about this is this and that. What do they do to each other? Cancel out. So all you have to do is 42 times 3, and that's your answer on it. You're going to get the same answer if you include it or not. So, all right. And so that's really it for gas stoichiometry. Tomorrow we'll probably do something like a gizmo. I have a gizmo or a FET. I need to figure out which one I'm going to use to kind of do that. So we'll do that just for some more practice with this kind of stuff. So there's some stuff with ideal gas law that we can practice. Thursday, I will give you the study guide for test 3, and we'll start working on that. Or tomorrow we'll start working on the study guide, and Thursday we'll do the gizmo, one way or the other. Yeah, well, the gizmo, I'll post it, and I'll post the Google Doc form as well. So, like, if you're not here, use the Google Doc. If you're here, I want it on paper. Yeah. So it just kind of depends. And then if you're not on Wednesday, just remind me to give you the study guide. And so we'll go through those and all of that. At this point in Chem 101, you should be able to answer all the questions. Now, that doesn't mean that you know how to, that you'll immediately see how to. So I'm going to give us time in class tomorrow. We have about 20 minutes today. If you want to start working on them, you can ask questions and I'll go through them. Yes, there's a lizard in the room. What? I've been trying to actually catch him, but he keeps running away from me. So I was trying to put him back outside, and he keeps running away from me every time I try to catch him. So yes, let me stop the video. Yeah.